Transition metals such as iron, copper, and nickel are found in a wide range of alloys commonly used in industry. One concern with the use of these alloys in industrial settings is the long-term potential for corrosion to weaken them and shorten their lifespans. But being able to predict the extent of metal loss within the actual surface environment of the material has long been considered by corrosion scientists to be the grand challenge. Currently, there is no corrosion model that can be used to predict corrosion of different metals and alloys over a wide range of solution conditions and time periods. This is because corrosion is a uniquely complicated system. Not only do we need to consider the electrochemical reactions at the metal surface, but we have to be concerned about the metal ions that go from the solid to the solution phase. We also need to be able to describe the different transport processes and chemical reactions that these metal ions can undergo once they are in solution, which change with time and solution conditions. Because of this, existing reaction kinetics don't work to predict corrosion in these systems. Recent research from our group has demonstrated that corrosion can be a nonlinear process, meaning that feedback loops between steps within the mechanism are possible. This is where the species that are produced by one reaction affect the rate or progress of another reaction in the system. These feedback loops generate periodic behavior that can't be described with existing rate models that focus on describing the overall process instead of the dynamics between the individual steps. So, to address this grand challenge of predicting corrosion in service environments, our group is focused on developing a corrosion mechanism and determining the parameters within the service environment that affect corrosion behavior, like pH, type and concentration of oxidant, and flow rate. Since we have a pretty good idea of the corrosion mechanism, I've been able to carefully and systematically design electrochemical experiments that can be used to extract rates and rate parameters for key steps within the mechanism. In an electrochemical experiment, the net current is related to the rate of the redox reactions and is dependent on time and potential, while the rate of other chemical and transport reactions are dependent on the solution environment. We can vary the transport, redox, and chemical environments and determine how they change the time-dependent behavior of the current. We can then examine the relationship between current and potential to get dynamic information that we can use to fine-tune rate and flux equations for different steps. We can also use the experimental information to validate the model at different stages of development. While this modeling work is just beginning, this mechanistic approach to corrosion rate models gets us one step closer to tackling the grand challenge of predictive corrosion modeling.